In our last video, I walked us through the oxidation number method for balancing redox reactions using the oxidation number method. Let's go through and do another example. In this example, we have the iodate ion reacting with the sulfur dioxide gas to create elemental iodine and the sulfate ion. Now, just like we saw in our previous example, there are definitively pairs here that seem to make sense. We have the iodine-containing compounds here, and we have the sulfur-containing compounds here. Now, before we go too deep into this, one thing that we want to make sure that we do is before we start getting into oxidation numbers and balancing charges and all that stuff, let's make sure that we've got equal numbers of our pairs on each side. So I can see here I've got 2 iodines here, but only 1 here. I'm going to need a second iodate ion to just balance out the iodines before I get anything else started. It turns out the sulfur is fine in that regard anyway. But the reason why I want to do that is I want to make sure that when it comes to evaluating the changes in oxidation numbers, that I'm doing it correctly and that I'm accounting for the fact that in the equation there are multiple atoms that are changing oxidation state, which means that multiples of those electrons are actually moving. So let's get into the oxidation numbers themselves then. For iodine and iodate, we're talking about a +5. For the oxygen here, it's still a -2. For the sulfur here, we're talking about a +4. And for the oxygen, once again, a -2. Iodine is an element here, so it's a 0 state. The sulfur is a +6 state. The oxygen is a -2 state. So if I follow this through and I look at it from that perspective, I can see that the iodine is changing from +5 to 0. Now, what we need to keep in mind is that +5 to 0 is happening twice because there are 2 iodines that are being converted. And so what that means in net is that the iodine in total is adding 10 electrons. And if I look at the sulfur, in the sulfur I see that I'm going from the +4 to +6 state. Well, that means that I am losing 2 electrons in the process. So in this scenario, we can see that the iodine is going to require 10 electrons, and the sulfur is going to be able to produce 2 of them. Now, how do we rectify that? Well, this is where it gets a little bit tricky. We have to make sure that all of the electrons that are being transferred all get used up. So to get 10 electrons, I need this sulfur reaction to happen 5 times. And so by happening 5 times, I now have 10 electrons that are being lost to match the 10 that were being gained. And so we've now hit the point where, as far as acid and base are concerned, we would have done it exactly the same way in both cases. And we would have ended up with the same result here. So let's take a look at the next step. The next step would be to evaluate the total charge on each side of the ledger. And so if I look at the iodine side, or the reactant side, I have 2 -1 charges from the iodates, and I have 5 0 charges from the SO2s. So the total charge on the reactant side is -2. On the product side, I have a 0 charge from the iodine, and I have 5 -2 charges from the sulfates for a total of a -10 charge. And so this is where our path diverges. In this path, we will either add hydrogen ions if we're in acid, or we will add hydroxide ions if we are in base. So let's do the acid first. To negate this, I would have to add 8 hydrogen ions. Adding 8 hydrogen ions would mean I'm adding 8 hydrogens. I don't have any hydrogens right now, so I need to add 4 waters to counterbalance it. And so the net solution, the net reaction in acid would be 2 iodates plus 5 SO2s plus 4 waters would give iodine and 5 sulfates and 8 hydrogen ions. And so this would be my balanced chemical equation if I were in acid solution. Now, if I'm in basic solution, all that changes, all that's different, is how we treat this step here in the middle. So just to reset, I had, let's get a different color here. I have -2 on the reactant side. I have -10 on the product side. Instead of adding hydrogen and water, I'm going to add hydroxide. So I need 8 hydroxides on this side. And to counterbalance the hydrogens that I added, I'm going to add 4 waters on that side. And so the net result in base, I would have still 2 iodate plus 5 SO2 plus 8 hydroxide yields iodine, 5 sulfate, and 4 water. And so that would be the balanced reaction for if I was in a base. And so the thing that we need to notice, look closely here, the skeleton is essentially the same. 2 iodates in each, 5 sulfur dioxides in each, 1 iodine molecule in each, 5 sulfate ions in each. What changes each time is if I'm in acid, I'm going to have hydrogen ions. In base, I'm going to have hydroxide ions. Let's take a look at one more example. This one we're only asked to balance in acid, so we don't have to worry about the divergence here. We can go straight into just balancing it out. Start by assigning oxidation states. For manganese, it is +2. For the bismuth in the bismuthate ion, it is +5. For the oxygen in that ion, it's -2. For the permanganate, we're looking at a +7 for manganese and a -2 for the oxygen, and the bismuth is a +3. So again, thinking about things in terms of pairs, my manganese goes from +2 to +7. And so we know that that is going to come with a loss of 5 electrons. And we can see that the bismuth is going from +5 to +3, +5 to +3, which means that it is adding 2 electrons. Now, here's again a case where we can see the number of electrons being lost does not equal the number of electrons being gained. And so what do we have to do about that? Well, it's simple. We have to find some kind of number, multiple, that allows both of those things to even out. What we're looking for in mathematical terms is the lowest common multiple. The lowest common multiple between 2 and 5 is 10. So to get the 10 electrons in the bismuth reaction, we're going to have it happen 5 times. And that'll give us 10 electrons in total. And for the manganese reaction, it's going to have to happen twice to give us that 10 electrons there. Now, we put those numbers in, 2 for the manganeses, 5 for the bismuths, and there we have our skeleton reaction. Everything's kind of set up from that standpoint. Now we need to evaluate charge. So split it down the middle. I have as charged 2 +2s for the manganese and 5 -1s for the bismuthate. +4 minus 5 is a -1 charge overall. And on the manganese side, I've got 2 -1 permanganates and 5 +3 bismuths. So total charge here is +13. Since I'm an acid, I need to only worry about the hydrogen ion. So I need to add this to the side that is least positive, which would be the reactant side. To turn a -1 into a +13, I would have to add 14 hydrogen ions. Adding 14 hydrogen ions would mean that I would need to add 14 hydrogens to this side, since there are none currently. And so that means 7 waters get added to this side. And so if I put it all together, it would be 2 manganese, 2 plus ions, reacting with 5 bismuthate ions and 14 hydrogen ions to make 2 permanganates, 5 bismuth 3 ions, and 7 waters. And so there you have it, your balanced redox reaction in acidic solution. Now, if you want more examples, there are more examples available in Blackboard. Otherwise, keep working hard at this. It's something that you just have to kind of work on to get better at, but it does improve over time. Have a good afternoon.